Take a deep breath. Let your mind settle like dust in slow gravity. Tonight we drift into the strangest questions physics has to offer. Not just what reality is, but why it behaves so strangely at its deepest levels. Before we begin, tell me, where in the world are you listening from? And what time is it there? You can be on one side of the universe. I'll be on the other. But if we were particles, quantum particles, somehow bound together by the quiet rules of entanglement, then what I do here would instantly affect you over there. No delay, no signal, no in-between, just an immediate connection that doesn't care about space, time, or the speed of light. Einstein called it spooky action at a distance, and even he didn't like it. It felt wrong. Too magical. Too uncomfortably intimate. But it's real. And it's one of the most quietly baffling phenomena in all of physics. Here's how it works. Take two particles. Link them in just the right way, through a shared origin, a delicate interaction, a mathematical dance. Once they're entangled, their states become interwoven. You can separate them across galaxies and still, measuring one tells you everything about the other. If one spins up, the other spins down. If one falls into this state, the other snaps into its opposite, no matter how far apart they've drifted. As if the universe itself keeps a private thread running between them. Always. And the truly unsettling part? This isn't about sending messages. You can't use it to communicate or break the rules of time. But it does suggest something deeper. That maybe space itself isn't the ultimate divider we think it is. That maybe, underneath it all, everything is quietly connected, folded together in a way we just can't see. Some physicists believe this hidden connection points to a deeper layer of reality. Something beneath the particles, beneath the fields, where distance and location don't exist. Just a relationship. Correlation. Pure connection. As if the universe didn't begin with individual objects floating in space, but with one thing gently splitting but never fully letting go. So as you close your eyes tonight, here's a quiet thought to carry with you. If two particles can stay bound across light years, if their dance never really ends, then what else might be connected in ways we haven't yet noticed? And what if you, right now, are more deeply entangled with the universe than you've ever imagined? Imagine a quiet room, a curtain pulled back, a single beam of light, soft and narrow, aimed at a wall with two tiny slits. On the other side, a blank screen waits to reveal what the light will do. If light were just a stream of particles, like tiny bullets, you'd expect two neat lines on the screen matching the two slits. But that's not what happens. Instead, the screen reveals a strange pattern. Bright and dark bands. A ripple like waves overlapping, building and canceling each other out. This is the interference pattern. A signature of something behaving like a wave. But here's where it gets unsettling. Now imagine we try to observe which slit the particle goes through. We set up a detector to quietly watch, to peek. And the moment we do, everything changes. The interference pattern disappears. The soft wave becomes a hard particle. The act of watching collapses the mystery into a single outcome. The experiment is simple. But the implications? Deeply strange. This is the heart of quantum mechanics and of one of its greatest mysteries. The observer changes the observed. Just by knowing, you alter reality. The particle seems to exist in a superposition. Many possibilities. Until it's measured. Until it's looked at. Until you decide to pay attention. So what does this mean? Some scientists suggest it's not consciousness itself that causes the change, but the measurement, the interaction, the entanglement with the environment. Others quietly wonder if there's something deeper at play. Something about awareness, about being seen, that turns possibilities into facts. That transforms the question what could be into what is. And here's where it becomes personal. Because the same mystery plays out every day, on a different scale. How often does your attention change a moment? How many possibilities shift the instant you decide to act, to observe, to engage? Is the universe at its core shaped not just by matter, but by attention? As you drift towards sleep, let this question settle quietly in your mind. If the universe behaves differently when no one's looking, then what does that say about the world you see? And what about the parts you're not watching? Imagine you're aboard a spaceship, gliding through deep space. The stars stretch around you in stillness, and far ahead lies the vast unknown. You push the throttle gently forward, accelerating faster, faster, faster. But no matter how much energy you pump into your ship, no matter how hard you push, there's a quiet, immovable barrier you can never cross. The speed of light. Light doesn't just move fast, it moves at the ultimate speed. Roughly 300,000 kilometers per second. It's not just a speed limit, it's the speed limit. Not set by technology but by the fabric of reality itself. And here's the strange part. The faster you try to go, the harder the universe pushes back. As you approach light speed, time begins to behave strangely. Slows down for you. Not metaphorically, literally. Your seconds stretch. Clocks on Earth tick faster than the ones inside your ship. Space itself compresses in the direction you're traveling, as if reality is folding under the strain. And your mass. It increases. Gently, relentlessly. The faster you move, the heavier you become. By the time you're flirting with light speed, you'd need infinite energy to move even an inch faster. Einstein didn't come up with these ideas as science fiction. He uncovered them as quiet consequences of the nature of space and time. To move faster than light isn't just hard. It's like trying to divide by zero. Breaks the math. It unravels causality. Events start flipping order. Cause and effect become a blur. Reality loses its shape. And yet, we see things in the universe that suggest the impossible. Quantum entanglement. Inflation at the beginning of time. Hypothetical particles that could exceed light speed. Tachyons, ghostly travelers we've never observed but still wonder about. But for now in our universe, nothing with mass can reach light's speed. Light is the fastest thing we know because it's massless. It has no inertia. No resistance to motion. It simply is. Light isn't racing through the universe. In a way, it defines the universe's pace. So as you gently drift towards sleep, consider this. Light doesn't just illuminate the cosmos. It silently outlines the very edges of possibility. It's the thread between now and then, here and there. A whisper from the structure of space-time itself, softly reminding us that even the fastest journeys have their limits. And yet, some boundaries are meant to be questioned. Let's move deeper into the next strange bend of reality. How moving fast slows down time. Could astronauts age slower than us? Imagine you're on a train moving near the speed of light. Outside your window, the stars stretch like threads of silver, and the world you left behind grows smaller with every passing second. Inside, everything feels normal. Your heart beats. You breathe. You blink. But for someone watching you from Earth, something strange is happening. Your time is slowing down. This isn't science fiction. It's the very real and very unsettling truth predicted by Einstein's theory of relativity. The faster you move through space, the slower you move through time. This is time dilation, the idea that time doesn't tick at the same rate for everyone. It stretches. It bends. It behaves differently depending on how fast you're moving and how close you are to massive objects like stars or black holes. In 1971, scientists tested this with atomic clocks. They placed one on a jet and left another on Earth. After just a few hours of high-speed flight, the two clocks no longer matched. The one on the plane ticked ever so slightly slower. A small difference, yes, but proof that time is not absolute. It bends to motion. Now imagine this. An astronaut travels to a star 10 light-years away at near light speed. To those on Earth, decades might pass. But for the astronaut, just a few years. They return home to find old friends aged, cities changed, and time quietly slipped away while they moved through it more slowly. To them, the journey felt like a blink. To Earth, A lifetime. Time, it seems, is not a river flowing steadily forward. It's a fabric. One that stretches and curves depending on how fast you pull it. And when you move fast enough, really fast, it lets you skip ahead. But here's the deeper question. If time can stretch, if it can be slowed, could it ever be stopped? Or even reversed? And if two people can live two different versions of now, what does that say about reality itself? Close your eyes. Let your breath slow. And as you drift further into thought, ask yourself, are we moving through time? Or is time moving through us? Let's continue our journey one heartbeat at a time. How can something exist in multiple states at once? Until we look at it. Imagine a coin spinning in midair. For that brief moment before it lands, it's not just heads or tails. It's both suspended in motion, undecided. Only when it hits the ground do we know the outcome. In the world we see every day, this is just probability. But in the strange realm of quantum physics, that suspended state isn't just a metaphor. It's real. This is the strange and beautiful concept of quantum superposition, where a particle doesn't choose a state until it's observed. It exists in all possible states at once. A single electron can spin both clockwise and counterclockwise. A photon can pass through two slits at the same time. It's not either slash or. It's both. Until we look. The moment we observe, the moment we measure, it all collapses into a single outcome. Reality, it seems, waits for our gaze to make up its mind. Physicists represent these possibilities using a wave function. A soft, rippling map of what could be. Left undisturbed, that wave contains every possibility. 1,000 branching paths, 100 versions of reality, all true, all overlapping. But measurement forces a decision. The wave collapses. Possibility becomes actuality. But why? What is it about observation that seems to rewrite the rules? Is it simply interaction? The intrusion of another particle, another force? Or is there something deeper, something consciousness might be connected to? Some interpretations, like the Copenhagen interpretation, tell us not to ask, what state was it in before we measured? Because they say that question doesn't make sense. Others, like the many worlds theory, suggest the wave function never collapses at all. Instead, the universe quietly splits, creating a separate world for every possible outcome. So in one world, the particle went left. In another, right. And somewhere, a version of you watched a different result unfold. As you gently drift into sleep, let this idea rest in your thoughts. If particles can exist in multiple states at once, what does that say about choice, about reality, about you? And if possibilities are real, at least until we observe, how many unseen paths might be quietly existing around you, right now? Does reality behave differently when no one's watching? Imagine a tree falling in a forest, deep in the wilderness, with no one around to hear it. Does it make a sound? Now take that question, flip it, magnify it, and aim it at the tiniest scales of the universe. Not trees but particles. Not sound but existence itself. In the shadowy realm of quantum mechanics, there's a quiet, unsettling idea known as the observer effect. It suggests that simply observing something, not touching it, not interacting with it physically, just watching, can change what it is. It began with a simple experiment. Scientists fired tiny particles, like electrons, toward a screen with two slits. When no one looked, the particles behaved like waves, spreading out and creating an interference pattern on the other side, as if each particle passed through both slits at once. But when scientists tried to measure which slit the particle actually went through, just to peek, just to check, the pattern changed. The interference vanished. The particle suddenly acted like it had only gone through one slit. It was as if the particle knew it was being watched, and changed its behavior accordingly. That's not just strange. It's deeply disturbing, because it hints that reality at its most fundamental level may not be fixed. That things don't settle into a clear state until we look at them, until we ask, until we observe. But what counts as observation? A human eye? A machine? Consciousness itself? No one knows. Some scientists propose it's all about interaction. When a measuring device exchanges information with a particle, things change. Others quietly whisper that consciousness itself may play a role, that perhaps awareness is more deeply entangled with reality than we ever imagined. It's not just a physics problem. It's a philosophical one. A metaphysical one. Because if observation changes reality, what does that say about the world we don't see? About the infinite moments we never witness? About the version of you that exists when no one's looking? As you drift closer to sleep, let this soft mystery echo in your thoughts. Is the universe quietly unfinished until someone observes it? And if so, who or what is observing you? Why can't we ever truly know both the position and speed of a particle? Imagine standing in a quiet forest, watching a bird flutter from branch to branch. You can track its position with your eyes, or focus on how fast it's moving. But try doing both exactly and something slips away. One detail sharpens, the other blurs. Not because you aren't watching carefully enough, but because reality itself won't let you. This is the strange and unsettling truth behind Heisenberg's uncertainty principle. In the quantum world, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. It's not a limitation of our tools or technology. It's built into the very structure of reality. Try to pin down an electron's exact location and it stops behaving like a moving particle. Try to measure its motion and its location turns hazy like a smudge in space. It's as if nature has drawn a boundary, not with force but with mystery. A soft quantum whisper saying, "You can't know everything at once." On large scales, we don't notice this uncertainty. A tennis ball, a planet, a train, they all behave just as we expect. But on the tiniest scales, the world begins to shimmer with possibility. It refuses to be nailed down. Particles jitter, flicker, exist not as dots but as clouds of probability. Some physicists have likened it to rolling dice you can never fully see. Others describe it as looking through a fogged-up window. You can make out shapes, motion, but never everything clearly at once. It's deeply humbling. The closer we look at reality, the more it seems to retreat behind a veil of probabilities and maybes. And yet, this principle isn't chaos. It's a quiet kind of order. One that hints that the universe values balance over certainty. Flow over fixation. As you let your thoughts drift softly toward sleep, consider this. If even the tiniest pieces of the universe can never be fully pinned down, maybe it's okay that parts of our own lives feel uncertain too. Maybe uncertainty isn't a flaw in the system, but a sign that something deeper is still at play. How particles can pass through solid barriers, like ghosts through walls. Imagine placing a ball at the bottom of a hill. It doesn't have enough energy to roll over the top, so it stays put. Simple enough. But in the quantum world, things don't work like that. In the quiet, strange language of the universe's tiniest parts, even when something shouldn't be able to cross a barrier, it sometimes just does. This is the softly bizarre world of quantum tunneling, a phenomenon where a particle, like an electron, encounters a barrier it shouldn't be able to pass, and yet somehow appears on the other side. Not by smashing through, not by going around, but by simply existing there. As if the wall was never truly a wall at all. How is that possible? At the quantum level, particles aren't little dots. They're described by wave functions. These wave functions represent probability, shimmering clouds of where a particle might be, not where it definitely is. When a particle's wave function reaches a barrier, part of it leaks through. And in rare moments, the particle isn't just likely to be on the other side. It is. To us, it feels like a ghost walking through a wall. But to the universe, it's just normal. No laws are broken. No magic performed. Just the quiet indifference of a reality that's stranger than our minds are built to grasp. But the implications are anything but quiet. Quantum tunneling is why the sun shines. It's how nuclear fusion happens in the hearts of stars. It's the reason electrons can escape atoms. And in the world of quantum computing, it's being explored as a key to unimaginable processing power. And then there's something even more quietly unsettling. If a particle can tunnel through barriers that should stop it, what other boundaries might not be as real as they seem? Could the limits we believe in, between space and time, self and other, life and death, be just barriers our minds can't yet tunnel through? As you drift deeper into the quiet of your own mind, let that image settle softly. A particle gently slipping through a wall, not breaking it, not forcing it, just appearing on the other side. Maybe reality isn't solid at all. Maybe it's full of doorways we haven't yet learned to see. And maybe the universe is whispering that nothing, truly nothing, is impossible. Why even nothing in space is constantly bubbling with activity. Close your eyes and imagine nothing. No stars, no planets, no light. Just the deep blackness of empty space. Still silent, absolutely empty. But here's the twist. In the world of quantum physics, even nothing isn't truly empty. Zoom in closer, far beyond what your eyes or any telescope can see, and the illusion of stillness begins to fall apart. What seemed like a calm, empty void suddenly reveals itself as a restless ocean. Pairs of particles and antiparticles are blinking in and out of existence, popping into being and vanishing in the blink of a cosmic eye. These are called vacuum fluctuations, tiny, spontaneous eruptions of energy in what we once believed was true nothingness. According to quantum field theory, every inch of space is threaded with invisible fields. These fields aren't passive, they're alive with possibility. Even in their lowest energy state, they hum quietly with uncertainty. That hum is the quantum vacuum, and it's never truly still. Sometimes this bubbling background has real effects. These virtual particles, though fleeting, can influence the behavior of real ones. They create forces. They alter outcomes. They change the shape of reality. In fact, the Casimir Effect, a measurable force between two plates in a vacuum, is proof that this invisible dance is not just theory but a feature of our world. And it doesn't stop there. These quantum fluctuations might have shaped the universe itself. Some theories suggest that the entire cosmos, the galaxies, the stars, everything, could have emerged from one particularly large fluctuation in an ancient vacuum. In other words, the universe may have bloomed from almost nothing. So when we speak of empty space, it's not an absence. It's a stage. A restless, invisible theater where energy flickers in and out, quietly sculpting the structure of everything we know. As you begin to drift off tonight, consider this. The next time you stare into the blackness of the sky, you're not looking at nothing. You're witnessing an ocean of whispers, quiet, invisible, and always moving. And maybe, what seems silent is never truly still. Close your eyes and imagine the fabric of space. Not as smooth, calm, and endless, but as something wild. Something trembling. Something chaotic. Now zoom in. Past galaxies, atoms, quarks. Keep going. What do you find? Not silence. Not stillness. But a storm. At the smallest scale imaginable. Far below atoms, far beyond what our most powerful microscopes can see. Space is not flat and empty. It's not a blank canvas stretched across the universe. It's alive with energy. It's restless. Bubbly. This is what physicist John Wheeler called quantum foam. It's a strange name for an even stranger idea. That even the emptiest vacuum is a seething chaos of fleeting particles, popping into and out of existence like flickers in a dream. These ghostly ripples are caused by the uncertainty built into the quantum world, where nothing ever sits completely still, not even the vacuum of space. Imagine the surface of a boiling pot. Bubbles swell, burst, reform. Now imagine that same bubbling happening everywhere, constantly, even in places we consider completely empty. These aren't just particles, but distortions of space and time itself. Space down at this scale is so jittery, so unstable, that the very idea of position, of direction, of here and there starts to fall apart. Some physicists believe this foam might be the birthplace of everything, where space, time, and even matter begin. Others think it's a sign that our current understanding of physics is simply incomplete. That beneath the calm surface of the universe is a raging sea we barely comprehend. It also leads to strange implications. If quantum foam is real, then space itself has a grainy texture. Time may not flow smoothly. The constants of the universe might not be constant at all, but shifting slightly in the churn. And yet, despite its wildness, this foam is impossibly small. Smaller than a proton. Smaller than anything we can directly see. It's as if the universe hides its deepest chaos beneath layers of calm. So tonight, as your body settles and your thoughts begin to drift, hold this thought gently. Even in the quietest parts of space, something is always moving. Always bubbling. Always shifting beneath the surface. If the foundation of reality is this unstable, what does it say about everything we build upon it? At what point does possibility become reality? Imagine staring at a perfectly still pond, moments before a single pebble touches its surface. The water is calm. The ripple hasn't begun. But it could, at any second. In quantum mechanics, this is where everything begins. In a quiet stillness where reality itself exists not as a single truth, but as many possibilities. Particles, at their most fundamental level, don't behave like solid objects. They don't have exact positions or fixed speeds until we measure them. Instead, they exist in a strange haze of probability, a blur of potential outcomes. A particle could be here, or there, or somewhere in between. This isn't poetic metaphor. This is the literal math that defines how our universe behaves. Until we look, until we measure. This is the heart of the measurement problem, one of the most quietly haunting mysteries in modern physics. Why does the act of observing seem to collapse possibility into a single reality? Why does a particle that could be in 1,000 places suddenly snap into one exact spot the moment we check? Some interpretations suggest that the universe is constantly branching, each possibility forming a new world in a vast, invisible multiverse. In this view, all outcomes happen, but we only experience one. Others whisper about consciousness playing a role, that awareness itself might be the thing that shapes reality from the fog of the undefined. Then there are those who suggest we've misunderstood something more profound, that reality doesn't collapse at all, that it simply updates, that what we see is only a sliver of what truly is. But the truth is, we don't know. And that's what makes this question so powerful, because it gently forces us to confront the border between what is and what could be, between the shadowy quantum world and the sharp clarity of our lived experience. So as you begin to drift off, let yourself rest in this thought. If the universe only chooses a path when we look, how much of reality is waiting, quietly unformed, in the spaces we've never thought to observe? And what might be quietly watching us, waiting for us to be measured? Can something be both dead and alive? Until you check? Imagine a sealed box sitting quietly on a table. Inside it, a cat, a vial of poison, a radioactive atom, and a trigger mechanism. You don't hear any sound. You don't feel movement. The box is perfectly closed, perfectly silent. And here's the strange part. Until you open it, physics doesn't say whether the cat is alive or dead. It is both. This is the thought experiment that Erwin Schrödinger proposed in 1935, not to explain quantum physics, but to highlight how bizarre it really is. In the quantum world, particles can exist in a state called superposition, where they're in multiple states at once. A particle can be spinning clockwise and counterclockwise at the same time. It can be here and there, until something observes it. Then and only then it chooses. In the case of the cat, the radioactive atom has a 50% chance of decaying. If it decays, the poison is released and the cat dies. If it doesn't, the cat lives. But before you open the box, quantum physics doesn't allow us to say which happened. The atom has both decayed and not decayed. And so the cat bizarrely is both dead and alive. Not metaphorically. Literally. This leads to unsettling questions about the nature of reality. Does observation actually create reality? Is the universe not real until something, or someone looks at it? And who or what is doing the observing? Some physicists believe this is just a quirk of interpretation, that the cat isn't really in two states, only our knowledge is uncertain. But others argue that the wave function, the mathematical description of quantum reality, is real. And if that's true, then reality is fundamentally probabilistic until you interact with it. It means that until you experience a moment, see it, feel it, measure it, it's not locked in. Possibility lives in the silence, in the unopened box, in the breath before the choice is made. So tonight, as you close your eyes and drift into the dreamlike logic of quantum mystery, consider this: how much of your own reality exists only because you're looking at it? And what might be quietly waiting behind the boxes you haven't yet opened? Let's keep drifting. The quantum world has many more secrets to reveal. Imagine standing on a quiet train platform at dusk. A train rushes past, its lights flickering in the fading light. Just as it reaches the center of the platform, lightning strikes both ends of the train. Two sudden flashes that light up the sky. To you standing still, the bolts appear perfectly simultaneous. But to someone riding the train, the story unfolds very differently. Because they're moving forward, they see the bolt at the front before the one at the back. Same event. Same universe. But different realities. This is the strange beauty of Einstein's relativity of simultaneity. The idea that now isn't the same for everyone. What one observer sees as two events happening at the exact same time, another, moving at a different speed or location, may experience them as happening at different times entirely. There is no single absolute now that binds us all. In a universe where light defines the ultimate speed limit, time itself becomes elastic. Events that seem locked together in your frame of reference can unravel into different sequences for someone else. And that isn't an illusion or a trick of perspective. It's how reality works. This concept challenges one of our most deeply held assumptions, that time flows equally for everyone everywhere. Instead, time and space bend quietly with motion. They're interwoven, relative, subjective. Two observers can disagree about the order of things, and both be entirely right. This has real implications. For astronauts traveling near the speed of light, for GPS satellites constantly adjusting their internal clocks to sync with ours, for our very understanding of cause and effect. But it also whispers something more human. If time itself depends on where you are and how fast you're moving, then perhaps perspective shapes more than just what we see. It shapes when we see. Two people looking at the same event may never truly agree on the moment it happened. As you drift into sleep, let that idea settle in your thoughts. In a universe where simultaneity is relative, even shared experiences are quietly personal. And maybe, just maybe, that's the true nature of time. Not a single thread, but many gently overlapping. Let's move on to another quiet bend in the fabric of reality. Why does time only move forward, not backward? Imagine watching a teacup fall from a table. It hits the ground and shatters, ceramic shards skittering across the floor. The sound echoes. The chaos feels final. Now imagine the reverse. The pieces tremble, slide back together, leap from the floor, and reform perfectly on the edge of the table. Unbroken, untouched. It's not impossible by the laws of physics, but it never happens. Welcome to the mystery of the arrow of time, the gentle but relentless direction in which time flows. Forward. Always forward. Every law of physics, from gravity to electromagnetism, works equally well backward and forward in time. Mathematically, there's no reason you couldn't unbreak that teacup. And yet, life doesn't work that way. We remember the past, not the future. Age. We don't grow younger. Suns burn out. Stars die. Coffee cools. Nothing spontaneously rewinds. So what draws this invisible arrow? The answer, softly nestled into the heart of thermodynamics, is entropy. Entropy is a measure of disorder. And the second law of thermodynamics tells us that in a closed system, disorder always increases. That's why broken cups don't reassemble, why heat spreads instead of concentrating, why the past feels ordered and the future uncertain. Time, in this sense, flows in the direction where entropy grows. But here's the unsettling twist. No one fully knows why the universe began in such a low-entropy, highly ordered state. The Big Bang should have created chaos. Instead, it was precise, so precise that its structure allows for stars, planets, and life. If time flows forward because entropy increases, then the very direction of time might be set by a condition we don't yet understand. Some physicists quietly speculate that the arrow of time might even reverse in far-flung regions of the universe, or in other universes altogether. Others wonder whether our perception of time is just that, perception, a trick of memory, a bias of biology. And so, as you drift toward sleep, consider this. Every moment you've lived, every breath, every word spoken, has flowed in a single quiet direction. Not because it must, but because the universe gently insists. But what if, somewhere out there, time does run backward? What would it feel like to wake up before you fall asleep? Let's continue deeper into time and the questions it leaves behind. Close your eyes and imagine this. You're sitting in a humming time machine, fingers trembling slightly above the controls. You've set the date, decades into the past, to a time before your parents were ever born. Your mission? Find your grandfather and stop him from ever meeting your grandmother. You step out. The world feels different, simpler, slower. You find him easily, young, unaware of what's coming. You act. Gently, firmly. He never meets her. Your parents are never born. Neither are you. But wait, if you were never born, how did you travel back in time in the first place? That's the haunting loop of the grandfather paradox. A softly whispered contradiction wrapped in logic, bound by time. It's the kind of puzzle that seems simple on the surface, but the deeper you fall into it, the more it spirals into something unsettlingly impossible. The paradox strikes at the heart of causality, that delicate chain of cause and effect that holds reality together. If you prevent your own birth, you couldn't have existed to travel back in time. But if you didn't go back, then your grandfather did meet your grandmother. And you do exist, which means you could go back and stop it all over again. A feedback loop. A snake gently devouring its own tail. Scientists have proposed different ways to escape this temporal trap. Some theories suggest time might be more flexible than we think, capable of branching off into alternate realities. In that case, the moment you act in the past, you create a new timeline. One where you were never born. But the original timeline, the one you came from, still exists somewhere untouched. Others argue that the universe somehow self-corrects, preventing paradoxes before they happen. That maybe, no matter how hard you try, you'll never quite manage to stop that meeting from happening. A car might stall. A door might close. Coincidences aligning to quietly preserve the timeline, like a story that refuses to be rewritten. But no one knows for sure. Time travel remains a fantasy. But the paradox it reveals is very real. Our understanding of time, choice, and consequence may be far less linear than we imagine. So as you drift into sleep, let this question settle gently over your thoughts. If the past could be changed, would the future resist? And if time has rules we don't understand, are we living them every day without even knowing it? Let's continue deeper into this strange fabric of time. Imagine walking down a hallway that slowly curves until, without even realizing it, you find yourself back where you started. But here's the twist: you're not just looping in space, you're looping in time. This is the strange and softly mind-bending idea behind closed time-like curves. A prediction buried deep within Einstein's theory of general relativity. These curves suggest that under the right conditions, perhaps near a rotating black hole or inside a wormhole, the fabric of space and time might loop back on itself, allowing someone to return to the past, not metaphorically but literally. It's not just science fiction. Mathematically, these curves are allowed. They're real solutions to Einstein's field equations. In theory, if you were to enter one, you could travel into your own past. You could meet yourself, change things, or become stuck in a cycle, looping endlessly like a needle caught in the same groove of a record, playing the same moment again and again. But here's where the unease sets in. If time can loop, what happens to cause and effect? If you prevent an event that led you to travel back in time in the first place, what now? Do you vanish? Does the universe unravel? Do paradoxes ripple outward, breaking the logic of reality itself? Physicists don't know. Some suggest that the universe might self-correct, that timelines somehow heal themselves, avoiding paradoxes through unseen adjustments. Others believe we'd simply split into multiple timelines, branching off into separate versions of reality where each possibility quietly plays out. And still, some argue that nature must have a hidden law we haven't discovered yet, something that softly but firmly prohibits these loops from ever becoming real. The deeper we go, the stranger it gets. There's a haunting beauty to the idea that time is not a straight line but a curve. A loop, a spiral, a folded page in a book we thought we understood. If closed time-like curves do exist, then the past, present, and future are not distant shores, but touching edges of the same circle. So as you gently drift into sleep, ask yourself, if time could loop, if you could walk backward through your memories, touch yesterday like a page still warm, would you change anything? And if you did, would you still be you when the loop returned? Let's keep floating, deeper into the fabric of reality, where even time is a mystery. Could everything in 3D space actually be encoded on a 2D surface? Imagine standing in front of a mirror. Not just any mirror, but one that doesn't reflect your face. It stores it. Not visually, but fundamentally. Every detail of who you are, everything that makes you you, your thoughts, your memories, your very atoms, somehow flattened and recorded on a surface that only looks like a reflection. Now imagine this mirror is the boundary of the universe itself. This is the unsettling idea behind the holographic principle, one of the most mind-bending concepts in theoretical physics. It quietly suggests that our three-dimensional reality might not be the full story. Instead, everything we see, feel, and experience, stars, planets, people, time, might be a projection from a two-dimensional surface far beyond what we can perceive. The idea first emerged from black hole physics. When something falls into a black hole, its information, the blueprint of what it was, seems to disappear. But Stephen Hawking and others realized something strange. The information might not vanish into the abyss. It might be encoded on the black hole's surface area, not its volume. Like a cosmic hard drive, its skin might hold the secrets of everything it swallowed. That was the spark. The next leap came when scientists wondered, what if that same trick applies to the entire universe? In other words, maybe the 3D world we live in is just the hologram. A rich, immersive projection of information stored on a distant 2D boundary we'll never see. Just as a 2D holographic film can produce a 3D image when lit the right way, perhaps the universe is a shimmering illusion, deep, textured, and seemingly solid, yet emerging from something profoundly simpler underneath. This doesn't mean the universe isn't real. But it does mean that what we think of as space and depth and position could be emergent, like the weather is to air pressure and heat. It's real, but it comes from something deeper. As you sink softly into this thought, let your mind drift. If the universe is a hologram, what are you? A flicker of light on a surface? A pattern etched into cosmic code? Or something even stranger? An echo from a place your senses can never touch? And if reality itself is a projection, Who or what is shining the light? Does a black hole destroy information, or store it in strange ways? Imagine writing a letter, an intimate, detailed account of your life, and tossing it into a fireplace. The flames devour the paper, turning it to smoke and ash. To your eyes, it's gone. But physics tells us something quietly profound. Information is never truly lost. Even in fire, the atoms remain scattered and transformed, but still present in the universe. Now imagine tossing that same letter into a black hole. Unlike the fire, a black hole is more than just destruction. It's an end of visibility. Everything that crosses its event horizon, whether it's matter, light, or the memory of what it once was, disappears from the universe as we know it. Nothing comes back. No light. No signal. No trace. And that's where the paradox begins. Quantum mechanics, our most reliable theory of the small, says that information cannot be lost. Ever. But general relativity, the theory that governs the large, says that black holes trap and eventually destroy anything that falls in, including its information. The two great pillars of modern physics don't agree. This is the information paradox, one of the most quietly disturbing puzzles in all of science. Stephen Hawking once proposed that black holes slowly evaporate over unimaginable stretches of time, through something called Hawking radiation. But this radiation, as we understand it, appears random. Tells us nothing about what the black hole swallowed. If the black hole vanishes and the information isn't encoded in that final exhale, then it's gone. That violates the very heart of quantum law. So where does the information go? Some physicists suggest it's never really lost. It might be imprinted subtly on the event horizon like a hologram. Others think the information leaks out through the radiation in deeply scrambled form. Still others propose that the information might escape into a baby universe, unreachable from ours. Each theory whispers a different possibility, but none have yet quieted the paradox. And what makes this truly unsettling is what it means for you, for all of us. If information can vanish, if the past can be erased without a trace, then our memories, our choices, even our identities might not be as permanent as we believe. It suggests a universe where stories don't have endings, they just dissolve. As you drift off to sleep, consider this soft mystery. If black holes challenge the idea of permanence, could there be things in your life too that feel gone, but are quietly preserved in ways you cannot yet see? Let's keep falling deeper. The universe still has secrets to share. Why everything we think of as particles are just excitations in invisible fields. Imagine just for a moment that the universe isn't made of things, but of vibrations. That instead of tiny marbles bouncing around space, the building blocks of reality are like ripples on an unseen ocean. And what we call particles, electrons, photons, quarks, are simply the shimmering crests of those invisible waves. This is the strange, elegant heart of quantum field theory. It tells us that for every type of particle in the universe, there is a corresponding quantum field stretched out across all of space. Silent, invisible, and omnipresent. Even in the deepest vacuum, these fields are there. Always. Every particle you've ever heard of isn't a tiny thing zipping around on its own. It's an excitation, a disturbance, a brief flicker of energy in one of these underlying fields. An electron is just a ripple in the electron field. The photon? A ripple in the electromagnetic field. Everything we think of as solid, tangible, real, is simply energy rising and falling in vast, intangible oceans. What's even more surreal is that these fields overlap, interact, speak to each other in the quiet language of probability. Where one field fluctuates, another might answer. When you feel warmth from sunlight, you're not being touched by particles in the traditional sense. You're being bathed in countless tiny tremors of a vibrating field. And here's where the dream deepens. These fields don't go away. They don't fade when particles vanish. They remain beneath everything, always ready to rise again, like an ocean waiting for wind. It's a quiet unification of everything: forces, matter, even light, reimagined not as separate things, but as different patterns in a universal fabric. As you drift towards sleep, let that settle in your thoughts. What we call reality may not be made of objects at all, but of music. Of fields that hum and resonate, singing matter into existence. You, me, the stars, each just a fleeting note in the grand quantum symphony of the cosmos. And if all of existence is a kind of vibration, what song is the universe playing right now? Let's float gently forward, deeper into the fabric, and see what else the silence is made of. Imagine for a moment that this life you're living, the choices you've made, the path you've walked, the version of you reading this right now, is just one of countless versions quietly unfolding in other corners of reality. In one, you turned left instead of right. In another, you never moved away. In yet another, you never existed at all. This is the unsettling, beautiful idea behind the multiverse hypothesis. In quantum mechanics, every time a particle is faced with multiple possibilities, left or right, up or down, it doesn't simply choose one. Not at first. It exists in all possible states at once until it's observed. Then it collapses into just one. But what if it never truly collapses at all? What if every possible outcome still plays out, just not here, not in this version of reality? Some scientists, especially those who lean into the many worlds interpretation, suggest that each decision, each quantum event, causes the universe to split, subtly, silently, into separate timelines. One for every possibility. One where the coin landed heads. One where it landed tails. One where you stayed. One where you left. Suddenly, the universe is no longer singular. It's layered, branching, infinite. Every version of every moment exists, somewhere. In this view, you are not just you. You're a chorus of selves echoing across realities. Each version born from a different decision, a different roll of the quantum dice. And each one thinks it's the only one. What's perhaps most haunting is how this idea might never be proven. We can't observe these other universes directly. They exist, if they exist, behind a veil we can't pull back. But mathematically, theoretically, they're possible. Even likely. And so you're left with a gentle question, one that lingers like soft static at the edge of consciousness. If infinite versions of you exist, which one are you now? The brave one? The hesitant one? The lucky one? The lost one? And if some version of you is living out the life you only dreamed of, is that version dreaming of yours? Let's drift deeper. There are more strange truths softly waiting beyond the veil. Imagine two twins born from the same spark, created together perfectly in sync. Now imagine sending one to the farthest corner of the universe, billions of light years away, and keeping the other close to Earth. You flip one's state, and instantly, without a whisper of delay, the other flips too. No message was sent. No signal traveled between them. And yet, it happens. Simultaneously. Einstein called it spooky action at a distance. And even he was unsettled by it. This is quantum entanglement, one of the strangest, most mind-bending behaviors ever observed in physics. When two particles become entangled, their properties become linked, so that the state of one instantly determines the state of the other, no matter how far apart they are. It defies common sense. It seems to violate the universal speed limit, the speed of light. And it raises a haunting question. Is the universe secretly connected in ways we can't see? What's even more unnerving is that it works. We've tested it again and again in laboratories all over the world. We've entangled photons and electrons and even small molecules. We've separated them by kilometers, by satellites in space. And every time the eerie coordination remains. One particle knows what the other is doing, instantly. But how? Some physicists believe there's no message passing between them at all. Instead, the universe isn't local. It doesn't play by the rules of here and there. It's more like a single woven tapestry. tug on one thread and the whole pattern subtly shifts. In this view, distance is just an illusion, and entangled particles are not communicating, they're simply revealing a shared truth, one that was always there. Others suggest that reality only decides when we look. Until we observe one particle, both exist in a kind of suspended possibility. And the moment we check one, the universe subtly rewrites the outcome of the other to maintain consistency, as if the cosmos itself is playing along with the script, improvising as it goes. No one truly knows. As you sink deeper into stillness, consider this. If the smallest parts of reality can remain connected across impossible distances, what else might be linked in ways we haven't yet understood? Thoughts, choices, lives? Maybe the universe is less about separation, and more about quiet, hidden entanglement. And maybe, just maybe, everything is still holding hands, no matter how far it seems. Could exotic matter allow tunnels through space and time? Picture a folded sheet of paper. On one end, you place a dot labeled U. On the other, a distant galaxy. Normally, it would take light millions of years to travel from one dot to the other. But now, fold the paper so the dots touch. Suddenly, the journey is instantaneous. This is the idea behind a wormhole, a shortcut through the fabric of space and time. First predicted by Einstein and Nathan Rosen, wormholes are theoretical tunnels that could connect two distant points in the universe, or maybe even two different times. But there's a catch. Nature doesn't seem to build wormholes freely. To hold one open, you need something the universe doesn't like to offer: negative energy. Negative energy sounds like science fiction, but it's a real concept in quantum physics. Unlike the positive energy that powers stars and fuels motion, negative energy behaves strangely. It can exert repulsive gravity, pushing things apart instead of pulling them together. Theoretically, if you could gather enough of it, you might be able to keep a wormhole stable, stop it from collapsing in on itself before anything could pass through. Where would you even find such a thing? Some researchers point to something called the Casimir Effect, a bizarre quantum phenomenon where two metal plates, placed incredibly close together in a vacuum, experience a force pulling them inward. This force is believed to arise from a negative energy density between the plates. Tiny, fleeting, but real. The math works. The physics, maybe. But the engineering? Beyond anything we can do. Still, the implications are staggering. If wormholes can be stabilized, they could offer more than shortcuts. They might allow time travel too. Step through one end in 2025, emerge from the other in 1971. Or in a parallel universe. Or in a reality where you never asked the questions you're asking now. But there are risks. Some theories suggest wormholes would be wildly unstable, collapsing the moment anything passed through. Others warn of feedback loops and paradoxes, or worse, that using one could ripple chaos through spacetime itself. As you lay back, drifting deeper into thought, ask yourself, if there were a door in the universe, something that allowed you to escape space or time or both, would you walk through it? And if someone else already has, would we even know? Imagine you're in a completely empty room. No sound. No air. No light. A perfect vacuum. Now place two tiny metal plates inside, so close together they're barely a hair's width apart. You walk away expecting nothing to happen. But when you return, you find something strange. The plates have moved, ever so slightly closer together. As if something invisible, something impossible, was gently pushing them inward. This is the Casimir Effect. And it reveals something astonishing. Even nothing isn't truly nothing. In quantum physics, the vacuum of space isn't an empty void. It's alive with activity, tiny restless fluctuations bubbling in and out of existence. These are virtual particles, pairs of energy that flicker into being and vanish just as quickly. They emerge from the quantum foam, everywhere, all the time, even in what appears to be total emptiness. When two plates are placed extremely close together, They block certain wavelengths of these fluctuations. Outside the plates, the full chaos of quantum energy continues. But between them, only a limited set of vibrations can exist. And this imbalance, this subtle difference in the pressure of nothing, creates a very real force. It pushes the plates together, gently, quietly, as if space itself is breathing between them. You might wonder, how can empty space exert pressure? How can the absence of something create a measurable effect? It's a glimpse into the strange truth that reality isn't made of solid objects, but of fields and energies we barely understand. Forces emerge from imbalances we can't see. Movement arises not from contact but from possibility. It's as if the universe is playing an invisible symphony, and even silence has a role to play. This eerie force has been measured in laboratories. Real. But it feels like something out of fiction. A gentle push from the void, a ghostly breath from the fabric of reality itself. As you begin to drift off, imagine the spaces between everything, between atoms, between thoughts, between stars, aren't empty at all. They're quietly alive, restless, whispering. And if nothingness holds this much mystery, what else have we overlooked simply because we couldn't see it? Let's drift a little deeper. The universe is still softly humming. Is there a smallest possible unit of space? Imagine zooming in. Closer and closer, past skin, past cells, past molecules and atoms, into a realm where nothing looks solid anymore. Particles shimmer like ghosts. They aren't little marbles. They're clouds of probability, hints of existence. You keep going. Smaller still. Into a world beneath what even the most powerful microscopes could ever hope to see. Eventually you hit a wall. Not a physical wall but a fundamental one. A limit. The point at which space itself might stop being smooth and begins to look grainy. That wall is called the Planck Length. It's the smallest measurement of space that has any physical meaning. Roughly 1.6 x 10 superscript 3 meters. To give that some scale, if a proton were blown up to the size of the observable universe, the Planck length would still be far, far smaller than a single grain of sand. At this scale, our familiar understanding of space and time begins to fall apart. The geometry of the universe becomes turbulent, chaotic. A bubbling foam of uncertainty and fluctuation. Scientists call it quantum foam, a strange, restless fabric underneath all things. This is the playground where gravity and quantum mechanics clash. Where space might not be continuous, but pixelated. Why can't we look smaller than this? Because below the Planck length our current physics simply breaks. We can't probe that far without requiring so much energy that we'd create a black hole just trying to observe it. It's as if nature is telling us, this far and no farther. Some physicists suspect that if we ever understand what's truly happening at the Planck scale, we might finally unite the grand laws of Einstein with the quantum world. A theory of everything. But for now it remains a silent mystery. A quiet whisper beneath the noise of the universe. And as you drift deeper into thought, let yourself wonder. If there's a limit to how small things can get, could there also be a hidden structure underneath it all? One more fundamental than space, more primal than time? Let's keep falling, deeper still, into the paradoxes that lie beneath reality itself. What happens when we try to unite the big and the small, Einstein and quantum mechanics? Imagine two ancient languages carved into the fabric of the universe. One speaks of stars and galaxies, gravity and orbits, the smooth, majestic rhythm of the cosmos. This is the language of Einstein's general relativity. The other whispers of probabilities, uncertainty, and invisible particles popping in and out of existence. This is quantum mechanics. Each describes reality flawlessly in its own domain. But they do not speak to each other. And that silence is the heart of one of physics' greatest mysteries. When we look at the very large, massive stars, expanding space, the bending of time, we use Einstein's equations. When we explore the very small, electrons, atoms, particles dancing through fields, we turn to quantum theory. But what happens in places where both worlds collide? Where the massive becomes microscopic, like inside a black hole, or at the very first moment of the Big Bang? There the two theories break down. They clash like mismatched puzzle pieces. Gravity in Einstein's world is a smooth curve in space-time. But in the quantum realm, nothing is smooth. Everything jiggles. Everything fluctuates. Space itself becomes turbulent and uncertain. No longer a calm stage but an actor in the play. To reconcile these two truths, physicists search for something deeper. Quantum gravity. A theory that unites the vast and the minuscule. One of the most well-known attempts is string theory, which suggests that all particles are tiny vibrating strings, dancing in dimensions we can't see. Another is loop quantum gravity, which imagines space itself is made of tiny, discrete loops, like atoms of spacetime. But no one knows the answer yet. The quest for quantum gravity isn't just about math. It's about understanding the soul of the universe. What is space? What is time? Are they truly fundamental? Or do they emerge from something deeper, stranger, more primal? As you drift deeper into stillness, let your thoughts wander to the edge of black holes and the birth of creation itself. What happens when we pull back the last curtain? When the universe reveals its true voice, not in two competing languages, but in one quiet, perfect harmony. And if that unified theory exists, could it also whisper something unexpected about us? Why is space stretching? And what is it expanding into? Close your eyes for a moment and imagine dots on a balloon. As you gently inflate it, the dots drift away from each other. Not because they're moving on their own, but because the surface they sit on is stretching beneath them. Now look up at the night sky. Galaxies, like those dots, are drifting away from one another. Not because they're flying off into space, but because space itself is expanding. Not into anything. Not pushed by force. Simply stretching. Quietly. Continuously. Invisibly. But here's the unsettling part. We don't know why. Since Edwin Hubble's discovery in the 1920s, astronomers have known that the universe is expanding. But in 1998, something even stranger was uncovered. That expansion isn't slowing down like we expected. It's speeding up. It's accelerating. As if some invisible hand is quietly turning the dial, stretching space faster and faster. That invisible hand has a name: dark energy. But naming it doesn't mean we understand it. Dark energy could be a property of space itself. Could be a fifth force. A glitch in the structure of the vacuum. Or it could be a placeholder for something far stranger. Something we don't even have the language to describe yet. Now let's return to the balloon analogy. If space is expanding, we naturally ask, what is it expanding into? But this question, so simple and human, is built on intuition shaped by our limited, earthbound experiences. The truth is, space doesn't need anything to expand into. It's not expanding into a pre-existing void. It creates room as it grows. The distance between galaxies increases not because they're moving through space, but because there is more space between them than there was a moment ago. Reality is stretching from within. And here's where things get quietly terrifying. If space continues expanding at an accelerating rate, one day galaxies will drift so far apart that their light will never reach each other. The universe will become cold, dark, silent. A place where every island of matter is alone in its own bubble of existence. We call this quiet, distant future the heat death, not with fire but with stillness. As you drift into sleep, think about this. The sky above you isn't still. It's not static. The very fabric of reality is stretching, right now. And the further you look, the faster it moves away. Not into somewhere, but into something that wasn't there a moment ago. And maybe that's the most beautiful and haunting truth of all. Imagine standing in a perfectly still room. No wind. No movement. Just silence. Now imagine that despite the stillness, something subtle is pressing against you, softly, persistently, pushing you outward away from everything else. You can't see it. You can't hear it. But it's there. Always. Quietly expanding the space between all things. In cosmology, this invisible pressure has a name: the cosmological constant. First introduced by Albert Einstein, this tiny number was originally meant to keep the universe static, something he later called his biggest blunder. But decades later, when scientists discovered that the universe isn't just expanding but doing so faster and faster, the cosmological constant was quietly resurrected. It now represents the gentle push of dark energy, the unknown force behind our accelerating universe. But here's the strange part. The number is almost perfectly small. So small, in fact, that it baffles physicists. If it were even slightly larger, galaxies wouldn't have formed. Stars wouldn't exist. Life would never have had a chance. And if it were slightly smaller, the universe might have collapsed back in on itself long ago. It's balanced on the edge of a cosmic knife. Why should this one number, one tiny constant in the equations that describe everything, be so precisely tuned for a universe like ours? Some suggest it's a coincidence. Others quietly believe we live in one of many universes, each with different constants, and we simply happen to exist in the one where life is possible. A whisper of the multiverse idea. Still, the fine-tuning remains unsettling. It's as if reality itself was calibrated with care, as if the laws of physics were gently dialed in, not for life necessarily but for existence. And we're here caught in the space between too much and too little. As you drift into sleep, think about this. A single number, invisible and silent, might be the reason anything exists at all. And the fact that you're here right now thinking about it might be the strangest mystery of all. Let's keep going. There are still more quiet truths folded into the fabric of the cosmos. Is the universe slowly winding down towards stillness? Imagine lighting a candle in the dark. At first, the flame flickers brightly, dancing with energy and warmth. But give it time and the wax melts, the wick shortens, and eventually, inevitably, the flame goes out. Not because anything attacked it, but because it simply ran out of fuel. The energy it once held diffused into the room, into the air, until everything was the same temperature. Balanced. So, now take that quiet image and stretch it across the entire cosmos. This is the haunting concept of entropy, the universe's quiet tendency toward disorder. Not chaos exactly, but balance. A spreading out of energy. A leveling of differences. And it's not just a theory, it's one of the most fundamental principles of physics. Entropy is why hot coffee cools down in a cold room. Why stars burn through their fuel. Why everything, eventually, tends toward equilibrium. Over cosmic timescales, as galaxies age and stars die, the universe loses its ability to do work. Energy doesn't disappear, it just becomes less useful. More spread out. So, this leads to a chilling possibility: the heat death of the universe. A time so far into the future that it stretches the imagination. When all the stars have gone dark, black holes have evaporated, and even the atoms themselves have decayed. What's left is a vast, cold, silent universe. No warmth. No light. No motion. Just particles drifting aimlessly in an ocean of nothingness. Perfect equilibrium. Absolute stillness. But strangely, not destruction. Just silence. A kind of eternal twilight. The flame not blown out but gently allowed to fade, until it's impossible to tell it was ever burning at all. And as unsettling as that may sound, it raises deeper questions. Is this slow unwinding just the end of one chapter? Could something emerge from the quiet that follows? Or is the final destiny of everything simply rest? As your mind drifts deeper, consider this. If the universe began with a brilliant flash, what should we make of its plan to end not in fire but in a whisper? And if even stars fade, what small burning truths should we hold on to while they still shine? Close your eyes and try to remember a moment from long ago. Your childhood, a summer afternoon, a quiet conversation. It feels like a thread you can follow backward, doesn't it? As if time is a path laid out behind you, gently stretching into the past. And ahead, another path, uncertain, unwritten, waiting. But what if that path doesn't exist at all? What if time as we feel it, moving forward, ticking away, isn't fundamental to the universe? What if it's something that emerges only when enough things come together? In the strange world of theoretical physics, this idea is quietly gaining traction. Some physicists propose that time isn't a basic ingredient of reality like space, mass, or energy. Instead, it might arise, like a shadow, only when complex systems interact in certain ways. Like temperature isn't something one molecule has on its own, but something that appears only when billions of molecules move together. This idea is called emergent time, and it's deeply unsettling, because if time isn't fundamental, then it wasn't always there, and it might not always be. In the earliest moments of the universe, right after the Big Bang, time as we know it may not have existed yet. Just a strange, timeless sea of possibilities waiting to crystallize into order. And if time emerges only from certain conditions, could there be parts of reality hidden from us, where time flows differently, or doesn't flow at all? Think about dreams. Sometimes entire stories unfold in seconds. Or you look at the clock and find that an hour has vanished without a trace. We brush it off as a quirk of perception. But what if our minds, too, are only creating the sensation of time, constructing a story moment by moment from patterns we barely notice? If time can emerge, it can also dissolve. And that opens a deeper question. If time isn't real in the way we believe, then what is change? What is aging? What is memory? If there's no true forward movement, only a series of stacked configurations, frozen and timeless, then who are we really? As you drift into sleep, let that mystery echo softly in your thoughts. Not just where in time you are, but if time is even real at all. And if it isn't, what then is this moment? When we say, nothing, what does that even mean? Close your eyes for a moment and try to imagine absolute nothing. Not emptiness, not blackness, but the absence of everything. No space, no time, no sound, no silence. Not even darkness, because darkness still exists. Try to picture that, and you'll feel your mind recoil. Because the human brain isn't built to grasp what nothing really is. But in physics, nothing isn't so empty after all. Take space, for example. You might imagine that if we cleared away every planet, star, and particle, we'd be left with nothing. But that's not quite true. Even in the vacuum of deep space, reality isn't flat. It hums with invisible energy. Tiny particles flicker in and out of existence in the span of a blink. Not because something's broken, but because that's just how the quantum world behaves. This restless activity in the vacuum is called quantum fluctuations, and it means that even the deepest nothingness is something. And it gets weirder. Some theories suggest the universe itself may have emerged from this kind of nothing. A sudden, spontaneous fluctuation in a sea of zero. No trigger. No before. Just a quiet bubbling of quantum possibility that gave birth to everything. And yet, that nothing wasn't truly nothing in the way we imagine. It still had rules. It still had energy. It still had potential. This challenges not only how we define emptiness, but how we define existence. If nothing can give rise to everything, then maybe the line between absence and presence isn't as sharp as we think. And perhaps, nothing isn't the opposite of something. Maybe it's the quiet stage before something unfolds. A cosmic breath held in perfect stillness, waiting to exhale. So the next time you stare into a dark room or look up at a starless night sky, ask yourself this. What are you really looking at? Is it emptiness? Or is it the quiet, restless canvas from which everything, including you, once emerged? Let's keep drifting. There are still questions waiting in the dark.